Imagine that we know the position of a particle at two different times. What trajectory does the particle take between these 2 points? We need a differential equation for the position of the particle as a function of time. Such an equation exists, of course, and is called Newton's second law. In this video, we show how to derive Newton's second law from a deeper, or at least equivalent, principle. The principle is as follows. Draw all possible paths between the initial and final position of a particle. At each point on a trajectory, the particle will have a position and a velocity. Define a function called a Lagrangian that maps each point on a trajectory to a scalar. For a particle in the conservative force field, the Lagrangian is the kinetic energy minus the potential energy. Now define a function called the action that maps each trajectory to a real number. The action is the time integral of the Lagrangian over the trajectory. The action maps each trajectory to a different number, and the trajectory with the minimum or maximum action is the trajectory that the particle actually takes. Hence, to find the actual trajectory, we set the differential of action equal to 0, since the differential of a function is 0 when the function is at a local maximum or minimum. We will assume that the Lagrangian depends only on the position and velocity of the particle, and not explicitly on the time. The resulting equations that we get from setting the variation in action equal to 0 are called the Euler-Lagrange equations. To get Newton's second law, you just replace the Lagrangian in the Euler-Lagrange equations with whatever its expression is. Now let's derive the Euler-Lagrange equations. Since the action is a maximum or a minimum for the classical trajectory of the particle, we should make a small change in the action and set it equal to 0. The action maps trajectories to real numbers, but trajectories are functions because they map time to position and velocity. Therefore, the action maps functions to real numbers. Functions that map functions to real numbers are called functionals. A small change in a functional is denoted by a little delta, not a little d like with ordinary functions. Now explicitly write the expression for the action as the time integral of the Lagrangian. The variation operator can be brought inside the integral. The Lagrangian depends only on the position and velocity of a particle, not on the time. Thus, the variation in the Lagrangian can be written as a term due to variation in position plus a term due to the variation in velocity. Notice that we are writing a small change in position and velocity with a delta and not a d. This is to remind us that we are varying the trajectories x of t and x dot of t, since they are the independent variables of the action. As shown below, the variation in the velocity is equal to the time derivative of the variation in position. As we will also show below, we can integrate the second term by parts to move the time derivative around and pick up a minus sign. Next, factor out the variation in position. The only way for the integral to be 0 is to force the term in parentheses to be 0, because the variation in position is arbitrary. This is the Euler-Lagrange equations. If you were to replace the Lagrangian by the kinetic energy minus the potential energy, you would recover Newton's second law. It should be noted that the Euler-Lagrange equations hold for any system with n degrees of freedom, where each degree of freedom is described by a coordinate q sub I. If the Lagrangian can be written in terms of these generalized coordinates, then the equations of motion for the system are found by replacing the Lagrangian with whatever its expression is in the general Euler-Lagrange equations. We will now explicitly integrate by parts the second term in the variation of the action. The formula for the integration by parts is the integral of u dv equals uv minus the integral of v du. We let u equal the derivative of L with respect to x dot, v equals the time derivative of delta x dt, du equals the time derivative of the derivative of L with respect to x dot, dt, v equals delta v. Insert these into the formula for integration by parts. The first term on the right is 0 because the variation in position is 0 at the initial and final positions. That is, all trajectories have the same initial and final positions. Now we need to prove that the variation in velocity is the time derivative of the variation in position. Write the variation in x dot as the variation in the time derivative of x. Assume that the time derivative of x depends on some parameter a. then the variation in the time derivative of x can be written as the derivative with respect to a of the time derivative of x times the variation in a. Combine the derivatives, switch the order of differentiation, take out a time derivative. Notice that the derivative with respect to a of x times the variation in a is the variation in x. Thus we have proven that the variation in the time derivative of x is the time derivative of the variation in x.